Hi, welcome to this video lesson on patterns and relations, where we will explore using variables to describe patterns. Let's start by reviewing our learning and language goals. Our learning goals for this lesson are: I can explore the relationship between the two columns in a table of values. I can represent and describe patterns and relationships using graphs and tables. I can use a mathematical expression to represent a pattern. I can express a given problem as an equation in which a letter variable is used to represent an unknown number. And our language goals are: I can talk about patterns using words like relationship, pattern, expression, equation, and variable. Let's start by reviewing some key vocabulary and concepts. First, let's recall what an input-output machine is. It's an imaginary machine that performs operations on a number to produce another number. When we feed numbers into this imaginary machine, we're giving it inputs. And that makes sense, right? When we put a number in the machine, it's called an input. Then the machine is programmed to perform an operation, or more often, a series of operations on each input to give a specific output. And that word makes sense too, right? The machine puts out the new number, so we call that the output. Okay, input, output. All right, now we can give the machine any kind of input we want. It does what it's programmed to do, and it gives us the output. So let's say we program the machine to multiply by 5, then add 3. We can give the machine any input we like, and it's going to take that number, multiply it by 5, then add 3, and spit out the answer, which we call the output. If we imagine this input-output machine is attached to a printer, we can ask it to print out a list of a range of inputs and the corresponding outputs. We call this an input-output table. This table helps us to see the relationship between a series of inputs and the given outputs. Now, because the machine is only programmed to do one specific set of operations to each input, the relationship between any given input and its output always follows the same rule. So in the example I gave before, that rule is multiply by 5, then add 3. That relationship stays the same between every single input and its corresponding output. Now, when we look at input-output tables, we can find the pattern rule that describes the relationship between the input and the output. And this is called the function rule. Now, since the word function rule is a lot easier to say than the pattern rule that describes the relationship between the input and the output, you'll probably hear me say function rule more often than the alternative, just because it's quicker and easier. Okay, so now that we've refreshed our memory about inputs and outputs, let's review how to find the relationship between the input and output. In other words, how to find the function rule. Well, we start by finding out the pattern rule for the output column. This pattern rule gives us clues that we can use to find the relationship. If the pattern rule goes up, it's a clue that one of the operations is multiplication, because multiplication is an operation that gives us a bigger result. Okay, think of an example. 6 times 7 is 42. Now, 42 is bigger than either 6 or 7. So multiplication is giving us a bigger result. All right. One really important thing to remember about this, though, is that the amount of the change in the pattern rule for the output column tells us the number to multiply by. For example, if you notice a pattern in the output column that increases by 4 each time, that's a clue that the first part of the function rule is multiply by 4. Now, what if the pattern rule for the output column doesn't lead you to a good clue? That happens sometimes. And if it does, the next step is to look for other patterns that can help. For example, not all input columns go up by 1 each time. Sometimes they have a greater change, and that can be a clue. Also, we want to look across the rows from input to output. Do the numbers get bigger? If each input is less than its corresponding output, that's a clue that the operation is multiplication, because we're getting bigger, right? But if each input is greater than its corresponding output, then that's a clue that the operation is likely division. Let's give it a try together. Here's an input-output table. Our first step is to analyze the pattern in the output column to find out what operations we have to do to each input number to get the corresponding output numbers. Now, take a look at that pattern in that output column and see if you can find a pattern rule there. The output numbers go up by 5, and that's a clue that the input numbers are multiplied by 5. So at least one operation, probably the first one, is likely to be multiply the input number by 5. Our next step then is to test that out. We can choose any input number in the table to test, but let's go with 4, okay? So 4 times 5 equals 20, but the output should be 23, so the pattern rule doesn't work. Now, do we just give up, toss it out, and say, I can't do this? No, absolutely not. We got 20, and 20 is close to 23, so we're probably on the right track. The fact that we didn't get it right away just means that there's probably more than one operation in the relationship between the input and the output in the function rule. Let's try the same rule on another input. This time we'll go with 5. If we multiply the input by 5, what do we get? 25. Now our output should be 28. Shoot, we're not there, but don't spiral into despair, okay? We have discovered something really useful here. We did the same operation, multiply by 5, and we're off by 3 both times. And that's consistent, which tells me we're onto something. We have a pattern coming here, right? So if we multiply by 5 each time, we end up being short by 3 each time, okay? That means we end up at a number that is 3 less than what the input should be. So that is the beginning of a pattern, and that pattern tells us what the second operation in our pattern rule is. If we come out with a number that's 3 less than what the output should be each time, what do we need to do? Take a second to think about it, and then I want you to say it out loud. Did you say add 3? If you did, give yourself a huge pat on the back, because that's the right answer. We think the rule is multiply by 5, then add 3, but we need to try it out on different outputs to make sure that it does actually work. So let's give it a whirl with 6, all right? 6 times 5 is 30. 30 plus 3 is 33, and that's the output we want. So check it on a few other inputs, and if it holds up each time, then we can confidently say that we have found the function rule, or the rule that relates the input to the output. All right, that one was actually pretty easy, so let's try out these strategies on a problem that's a little bit harder. That's right, Abby's back. Remember, this is the one that I messed up on the Edpuzzle where I asked you to find the output if the input was 15, and it's like literally right there on the first line. Well, we never did actually go back and work on this problem, so let's do it together right now. So here's the problem. Abby made an input-output machine that uses 2 operations. We have the input-output table for Abby's machine as well. The question is, what is the relationship between the input and the output? In other words, what are the numbers and operations we need to do to go from input to output? Or put simply, what is the function rule? Now, the first problem we have here is that the values are out of order in the columns, which is probably what led to my mistake the first time I tried to do the problem with you guys on Edpuzzle. So the reason this is a problem is that you can't see what the pattern rule is for the input or output column if the values are out of order. See, it goes 6, 4, 7, 8, 5 in the output column. So it goes down, up, down. There's no pattern that we can discern there. So before we start, we need to put the values in the table in order from least to greatest. It's super important that you order each row, though. You don't want to separate the inputs and outputs and mix them up, or you will never figure it out. Okay, take a few minutes right now to copy out this table and reorder the rows from least to greatest. So you want to start with the smallest one and work your way up and end with the biggest one. But remember, when you're reordering, keep the rows together, okay? So keep the inputs with the outputs. If you mix up the inputs and the outputs, you're going to be hooped. You'll never be able to figure out the pattern. Pause the video here and work on reordering your table. Take a look at this new input-output table on the right. Does your reordered table look like this one? If not, pause the video again and fix it up. Okay, so let's follow our steps here again. Number one, look for a pattern in the output column. And great, I see one right away. It goes up by one each time, which actually is not very helpful. I don't think it's a clue that we should multiply the input by one because then all the inputs and outputs would be exactly the same. And clearly they're not. So we are going to have to look for some other patterns to see if we can figure out what our function rule is. Okay. Okay, now that I look more closely at the inputs and how they relate to the outputs, I can see that the input numbers are all greater than the output numbers. So that gives me a clue. What do you think the clue is if the values decrease between the input and the output? Take a second to think about that. Did you say division? If you did, give yourself a big pat on the back. Okay, so our next step is to take a look at the patterns in the input column. I noticed something here right away. Now, maybe it's just because I love the number 5 and I find 5s easy to work with, especially multiples of 5, but we can see that there's a pattern there. Starts at 5, increases by 5 each time. It's essentially just skip counting by 5, but our input values increase by 5. So that is another clue for us. Now we know we're looking at an operation that makes numbers smaller because of the relationship between the input and the output, and we see that there's a pattern in the input table where the numbers increase by 5 each time. Now that feels familiar to how the clues work if we're looking at a pattern in the output column. So if we saw this kind of pattern in an output column, we'd say it was a clue to multiply by 5. But this is the input column, and we already know that we need an operation that gives us a smaller result. So multiplication won't work because it makes things bigger. But hang on a second here. Division is the inverse operation for multiplication, and division gives a smaller result. So what if the function rule involves dividing by 5? So I'm going to test it out. 10 divided by 5 equals 2. Now, the output we're supposed to have is 5, so that's no dice on that as being the pattern rule just by itself. But we don't give up. We need to try again. Remember, if we get close but we're not right there, it's probably a clue that there is a second operation that we need to do. Let's test it out with another input, and let's do 15 this time. 15 divided by 5 is 3, but we need to be at 6. But hang on, I see a pattern. We're short by 3. Okay, if we're short by 3, then we know that that means we need to add 3. So our tentative pattern rule now is divide by 5, then add 3. But we need to test it out to make sure it works. Let's use 20 because, again, it's a nice round number. It's easy to work with. 20 divided by 5 equals 4. If we add 3 to that, we get 7. And let's try one more just to be sure. We'll go with 25. 25 divided by 5 equals 5. And if we add 3 to 5, we get 8. So we have found the pattern rule that relates the input to the output. In other words, we have found the function rule, and it is divide the input by 5, then add 3.